chapter 15 here. So we're going to do 15.5 today and next time. And maybe the class after that we'll have to kind of see how much progress we make. I didn't do as much as I planned on yesterday because second hour was almost entirely swallowed up by stuff. All right. The plan for this section for 15.5, we're going to deal with like the mathematics of finance. So like all of these are going to be all specifically applications of like exponential and logarithmic functions, but that's the idea here. So what we're going to talk about first is like interest as it applies to like an investment or something. So we're going to talk about two types of interest today. The first is simple interest. So our simple interest formula, FV is equal to PV times the quantity 1 plus Rn over 100. FV is the future value, PV is present value, R is your interest rate as a percentage, and N is the number of years. Keep in mind that if you wanted to convert that interest rate to a decimal, you just leave off the divide by 100 in the formula. That's all that 100 is doing, is converting your interest rate from percentage to decimal. But whatever, however you feel like doing it, I usually just leave it as a percentage and use the 100 in the formula. So it's pretty straightforward, just kind of a formula. Let's do an example problem here. If you invest $2,000 at a 6% interest rate, how much total money do you have in the account after 3 years? Notice that that interest rate doesn't contain the term compound, so we know we're talking about simple. We start by investing $2,000, that's like the present value, 6%, that's our interest rate. 3 years, that's our N. How much total money are we going to have? That's a future value. So when we plug this stuff in, we end up with $2,360. Now what's going on here in a simple interest situation is the interest is only being paid on the initial investment. So you're getting 6% interest on that $2,000 in year one, 6% interest on that $2,000 in year two, and so on and so forth. You're only getting paid on the initial investment. The other type of interest payment that you can have is compound interest. In compound interest, yep, you're getting paid on the account value at every year. So essentially you're getting paid interest on your interest. So our compound interest formula and I noticed that almost all of those variables are the same, except we have one extra there. That extra value is a K. Which represents the number of compounds per year. Now the K we're going to hide in the story problem by using words. So we might say something like 6% interest compounded weekly. How many weeks are in a year? 52. So in that case, K would be 52. Or if it said compounded monthly, K would be 12. Or compounded daily, K would be 365. Or compounded quarterly, K would be 4. You guys get the idea, right? So they're never going to come right out and tell you what the K is. They're going to hide it inside of a number or inside of a word. But like, I got it, Mr. Kulik. I can handle like how many months are in a year. No big deal. We figured that out in like first grade. All right, let's look at an example. You invest $2,000 at a 6% interest rate compounded. So notice that's in there, so we know we're using compound interest. Compounded annually. How much total money do you have in the account after 3 years? And then how much did you gain in interest? So again, I see a present value, I see an interest rate, I see an N. Annually, well, that's just K equals 1. So this is ostensibly the same problem as last time, but this time we're doing compound interest instead of simple. So I type this into my calculator, and out is going to spit $2,382.03. Why am I rounding it to 2 decimal places here? What are we talking about? Money. That's why I'm rounding to 2 decimal places, right? To the penny. Because I don't know about you, nobody's ever given me less than a penny change. Even though on the gas station they used to back in the day, they have like gas, 98.9 cents per gallon. I don't think they show that anymore, but they used to show the point on the cent, the decimal pennies on the gas station signs for the gallons per gas when I was a youngster. And yes, gas did cost like 98 cents a gallon when I was in high school. I know. All right. Everybody feel okay there? It also asks an additional question. How much did you gain in interest? Well, if I ended with $2,382.03 and I started with $2,000, everything that is the difference is just going to be the result of interest, right? So in general, regardless of what situation we're in, compound interest or simple interest or whatever, if I take that future value and I subtract off the starting value, that difference is just going to be the amount of interest paid, right? So in this case, $382.03. So if I look at these first two examples, the compound interest and the simple interest, not much difference, right? Like, what, $22 or something? $23.60 versus $23.82. Like, whoop-de-dee-doo, Mr. Kulik. I'm not that, like, so what? Not much. $22 over 3 years. That's not getting my attention. What if we did this over 50 years, though? So let's do the simple interest first. So $8,000 for 50 years at simple interest.
Excuse me. Classes are happening. Thank you.
And almost $37,000 with compound interest. Holy shimolians, now you have my attention. That's a big stinking difference. In general, which would we rather have? Give me that compound interest. I want that 37,000 versus 8,000. It's almost 5 times as much money. Yes, please sign me up for that one. And all that's happening there, the only difference is instead of $2,000 earning interest every year, it's the value in the account that's earning interest. Okay, so that's all that's happening, but boy, that adds up. Let me drop this in here real quick. We said this in Word, aloud, but I'm going to just drop it in here so it's in here. So when we talk about our Ks, these are your common words that we'll use to hide our Ks. Annually 1, semi-annually 2, quarterly 4, monthly 12, weekly 52, daily 365. So what I'd like to do next is I want to do a little example here to illustrate to us how much difference that number of compounds makes, right? So let's look at an example here. So it says Jean invests $800 in a 7% annual interest account. How much money will she have in her account after 5 years if the interest is compounded? And then we'll do this problem, 6 different ways: annually, semi-annually, quarterly, monthly, weekly, daily, to just get a feel for how big of a difference, if everything else stays the same, does the number of compounds per year make. Everybody's okay with that plan? All right. So we're just going to set this up one time in our calculator and just update the K each time. Shh. Okay, so the first one is 11/22/04. Now to go from one compound to two compounds, I'm just going to update those ones and turn them into twos. And looks like we picked up about 650. Not lighting the world on fire there, but like, you know, it's like 650 that I didn't have from before. I'm going to do this so I can do that a little easier. Okay. So going from 2 to 4, I don't know. I mean, going from 1 to 2, I picked up 650. I'd expect to pick up at least that much going from 2 to 4. I picked up 2 additional compounds. Let's see. Oh, this is less. Only picked up an additional $3.40 or so. It's a little disappointing. Okay, well, the next one is going to monthly, so 4 to 12, 8 additional compounds. Now that's got to make a bigger difference there, right? That's a lot more compounds. Oh, like $2.30. I am less than wowed by this so far. And from 12 to 52, okay, that's 40 more compounds. That's got to be something. That does something, right? Less than $1. Less than $1. Mr. Kulik, I would say I am so far underwhelmed. Yes. And they're, what, about less than a quarter? So the takeaway here, what we want to have noticed, more compounds per year is still better, but boy, it doesn't make that much of a difference, right? Going from one compound to 365 compounds over that same 5-year period really just changed by $13. So the takeaway, the number of compounds per year, I'm not stressing over that. What I would want to stress over is the time, is how long my investment stays there. That's the big thing. The longer I can keep that money in a compound interest account, what incredible benefit that is to me. All right, let's do a couple more examples. I think I have 2 more examples and we're going to be done with everything that I'm planning to do today. So this next one says Mara has $1,000 and places it in a savings account with a 6% annual interest compounded monthly. How long will it take before Mara has $4,000? Okay. So I see compounded, so I know we're doing compound interest. I have a present value. I have an interest rate. I see the K is 12. It's saying asking us how long, so that's an N. And then we have given some future value. So compound interest formula, and just fill them in. So notice, where is our variable located in our problem? It is in the exponent. To solve an equation where the variable is in the exponent, what do we need to use? Not a square root. Give you a hint, it starts with an L. A logarithm, that is correct. But before we can do that, we have to isolate the exponential part. So we'll just start by dividing by 2. Why did I write 2,000 here? It was a 1,000 in the problem. Yikes, Mr. Kulik. So I'll start by dividing by 1,000. Now, I could do the arithmetic and rewrite 1 plus 6 over 1,200 as like a decimal. I'm not going to bother with it because it's all just going to go into my calculator eventually anyway. So like, I'm just going to save myself the aggravation. What I am going to do now is take the log of both sides. The base for my logarithm, I remember I want to use the logarithm base that matches the base of my exponential. So the log base I'm going to use is 1 plus 6 over 1,200. So I'm going to do that to both sides. And I remember log base cancels exponent base, so pew pew. So to solve for n, then I just divide by 12 and it's calculator time. And again, I like to write it as times 1 over 12 in these log problems rather than divided by 12 because I feel like it's easier or it's clearer that I've got it in the way I want it on my calculator if I do it that way. So 1 over 12 times. Now, to type a log base into my calculator, I'm going to press the math button, scroll down to the bottom and select the log base command. And I can literally just write in the expression 1 plus 6 over 1,200. And I get that 23.16 is my number of years. Everybody feel okay there? Okay, one more example and we'll call our quits for today. The goal hopefully is by the end of this chapter or this section we've taught you how to become a millionaire though. That's the goal. Gwen has $600 to place in a savings account. What annual interest rate would she need compounded weekly if she wanted to have exactly $1,500 in 10 years. So again, I hear the compounded word, so I know I'm doing compound interest. I have a present value. We're looking for R. We're given a future value, and we have an N. So again, we'll just be plugging things in to start. Oh, weekly. Forgot to write down my K. Knew I was forgetting something. All right. So notice here, where is my variable located? It's not in the exponent anymore. In this problem, it's in the base of the exponential. What am I going to have to use to cancel out that exponent? Max? Now it's time for, well, not necessarily a square root, but a radical. Could be a root other than a square root, right? But now it's radical time. Yes, sir. So just like before, we'll start by getting the part with the exponent by itself. Now I recognize that 15/6 can reduce a little more, but like it's all going in my calculator anyways. I just dropped the zeros because it's less writing for me. Now, to cancel out that exponent of 520, what index does my radical need to have? 520. So I'm doing the 520th root to both sides. So far, so good. And we'll just subtract 1 from both sides. And then multiply by 5,200. And we are ready to get this guy into our calculator. Everybody feel okay? Notice that there's more simplifying I can do, but I don't care. It's all going into my calculator. I'm not going to try to make this more complicated than it needs to be. I'm just going to keep tacking stuff onto the other side until it's calculator time. Right? I don't want to make this problem yuckier than it needs to be. So I'm just going to now type this into my calculator exactly like it looks on my sheet of paper. To get that 520th root, reminder how to do that. I'm going to type in the index 520, and then I'm going to press math, and I'm going to pick command 5, where it has the radical where the index isn't defined. If I press enter, that 520 now becomes the index for my radical. I'll just do 15 divided by 6 and close my parenthesis. So I get 9.17 is my interest rate that I need. Everybody feel okay here? So again, the goal by the end of this section is to teach you how to become a millionaire. You have a huge advantage right now because you are 16, 17, 18 years old. You are 50 years from retirement age. With conservative savings, you can become a millionaire many times over before it's time to retire. But the key is you have time on your side. If you punt on this and don't bother to start really saving until you're 30, the ability to do that significantly restricted. So as we go on, we'll show you guys how to compute this and figure out like exactly how much do I need to save every year with a reasonable, like a conservative interest rate to become a millionaire. Because that's what we'd like. When we're done working, that we can live in the lap of luxury, off in our golden years, and have no worries about a collapsing Social Security system or anything else, because I took care of myself and I got this taken care of. I got it, Mr. Kulik. I'm good. I made sound financial decisions for the rest of my life. But the key is starting now. Okay. We'll continue on and show you how to plan an investment strategy. The terminology for that would be like an annuity, where you're making like the same savings, or saving the same amount of money every period, whether that's a month or a year or whatever. And we can look at how that's gonna, or how to solve for this is how much I want at the end. How much do I need to be saving every month or whatever? But it's not that much if you start now. It's not that much. So that's next time, though. Additionally, next time, we are going to do a lot of these calculations with our graphing calculator. You have a program built into your graphing calculator that'll be quite useful in doing this. So if you are not accustomed to bringing your graphing calculator with you to class, I strongly encourage you bring it next time, because the program you need to be able to practice on it a little bit to get good at using it. It's not difficult to use, but give a man a fish, you feed him for a day. You teach the man to fish, you feed him for their life. You got to practice it. You can't just see it once and be able to do it. Figuring it out on your own, and why is this giving me an error? What did I do wrong? Why is this number negative? What does that mean? We got to get used to doing that, and you just need some trial and error on those sort of things. But that's it for me. Right about 33 minutes there. So that's that. Seniors that are scheduled to take a final exam in this class, your review packet is due by the end of class on Thursday, next class. If you have it completed and you're like, I'm done, I want to get rid of this, I am happy to take it early. Anytime you have it done and you're ready to get rid of it, I will take it, no problem. If you are not done yet, that's fine. But I will warn you, seniors, please do your review. Do it well, do it yourself. It'll be extremely helpful to you on the exam if you've done it, and you've done it in a way that is pretty thorough, to where you can use those problems as guides to do future problems, right? This should not be a tremendously difficult exam if your study guide is well put together and you've done a good job on that. The goal for me when I wrote both of these things is to make it, if you do a good job on your review, it's almost impossible not to do reasonably well on the exam. But if you don't do your own review, if you just copy some answers from somebody else and turn that thing in, or it's just you have lists of answers with no accompanying work or explanation of how you did things, don't know how helpful that will be to you. and you could be in for a long 80 minutes. It is a real exam, but the study guide can make it way easier if you do a good job on that. So just, if you are scheduled to take the final exam, make sure that you've spent some time on that study guide and it's in good condition. At the end of the day on Thursday, I will post on My Notre Dame the key for the study guide. My suggestion to you before you turn it in to take some pictures. So if you're like, ooh, I boogered, number 7 and 13, that you can study those two problems particularly so that when you get to the exam, you're like, well, okay, I know this isn't going to be a lot of help what I have written down because I boogered it. So I'm going to make sure I know how to do those kind of problems or whatever. But that's it. Everybody feel okay? The plan for homeworks, let's see, what do you guys have? We've done up to 138 so far. You guys can now do 139 to 150. So that'll be the part of Sunday's problem set. Be 139 to 150. Those should be relatively easy. You're basically just plugging things into the simple and compound interest formulas like the example problems were and then solving. So that shouldn't be too big of a challenge, but that's that. Final questions for me before we sign out? Okie dokie, artichoke.